Mr. G here today to talk about our third lesson here in our unit on our math review and intro to Physics 11. And it's this idea that you may have heard about in chemistry already, the idea of significant figures. And to be quite honest, within the realms of sciences, significant figures are something that I tend to overlook, but that doesn't deny the fact that they are an important idea behind any physical measurement we make. So let me give you an example here. Let's say that I'm going to ask my cousin out in Ontario just exactly how far it is from Vancouver to Toronto. And they might come up and they might say, yeah, right on, it's 5,000 clicks. And, that would imply the idea that it is exactly 5 million meters. Now, we all know that we could go on Google Maps and we could type it in and maybe we'll get a different answer, and maybe they're going to try and break it right down to the kilometer. But you'll notice that we're not breaking it down into meters or centimeters or anything like that. And even within the kilometer, it's based upon a GPS type measurement. So we can't always be 100% sure that the measurement we make is exactly what we're saying. So this is this idea of significant figures, and in general, every measurement is going to have some certain level of uncertainty. So we're going to talk about that ad nauseum here in Physics 11, and this idea that every measurement we have to take into account the error, because as it propagates through our different calculations, it gets worse and worse. So when we're talking about significant figures, we're really talking about this idea of accuracy versus precision. And there is the classic idea behind this, and it comes down to these targets right here. So accuracy, when we're talking about accuracy, we really mean just how close this measured value is to what we expected it to be, or what the accepted value is. So if we take a look at the first target here, you'll notice we have this X right there, which is awfully close to the bullseye. That's a fairly accurate measurement. But you'll notice that these other measurements aren't necessarily near the bullseye. So when we're talking about that, we're really meaning this idea of precision. And what we mean by precision is just how reproducible the measurements are. So in our first target case here, you'll notice that we did get one awfully close, but relatively speaking, the other ones aren't that accurate. Now, if we look at the second target, you'll notice that we have a whole bunch of X's that are all nice and bunched together. From a precision perspective, we've been able to reproduce our measurement fairly consistently. However, we're looking for a big X right smack dab in the bullseye, which means our accuracy isn't necessarily that good. Again, we're looking for an accepted value. So you can think of the idea of what is the acceleration due to gravity, and we ended up with values over here. Maybe it's 10.2 meters per second squared, but really we were looking for something more around 9.8. So there's some sort of systematic error in there we would have to talk about in future discussions. Now, if we take a look at the third target, this is the money shot. That's what we're looking for. We have a precise set of measurements. We've been able to reproduce it a bunch of times, and it's centered around our accepted value, so our accuracy is quite high. So this over here, that's what we're shooting for, my friends. Exceptionally difficult, especially when we're dealing with older technologies within the classroom or in labs in general. So it's always nice to have the newest technology to really help us out with these types of measurements. Now, when we get into the whole idea of, well, how does significant figures play a role in this? Well, in general, the last digit is always uncertain. When we talk about the idea of, well, it's 23 centimeters, well, what does that mean? Do we actually know it is exactly 23, or is it 23.1 or 23.2, or, you just don't really know, right? So when we take a look at our recorded data, everything there is considered significant, but that last digit is really our best guess, so it's always deemed uncertain. When we're talking about measuring tools and the uncertainty associated with those, the golden rule here is that measuring instruments, unless listed otherwise, you can come up with classic examples like the digital balances, for example. Those ones have a better than half the smallest division in their error. So generally speaking, always go with half the smallest division. So if we're talking about a meter stick, the smallest division is a millimeter. Therefore, its accuracy has to be, or precision rather, has to be within half the smallest division, so half a millimeter. So all of your measurements with a meter stick should be able to be done down to half a millimeter. So let's actually get into the SigFig rules, and these will apply when you're reading a number initially, and of course when we get into the idea of the algebra and the arithmetic that we use these numbers in. These are all going to apply in somewhat of a chain rule. So if we take a look at the first rule here, all non-zero digits are considered significant. So if we look at this number 321, obviously that has 1, 2, 3 digits. There are 3 significant figures. If you take a look at number 2, zeros that occur between digits are significant. So notice again, we have a digit here, we have a digit there. There are zeros in between. Therefore, we have 1, 2, 3, 4 significant figures. So in that case, we had zeros in between 2 digits, but what happens now if we have the zeros after 2 digits? And if we take a look at rule number 3, in any non-decimal number, I'm going to underline that because that is super important. The numbers to the right of other digits are not significant. So you'll notice that we have a digit, and then we have these zeros to the right of the digits. That means we actually have 2 significant figures. Now, what does this mean by non-decimal number? I'll do a little aside here with a thought bubble. If you rewrite this number as 5200 decimal, now that's considered a decimal value. And when that's the case, this actually equals 4 sig figs. So the decimal is a key. Now you're going to find yourselves, especially for those of you that are going to be taking sig figs a little more seriously, you're going to be rewriting numbers in terms of number of sig figs. So if you need to write a number like 5200 in terms of 4 sig figs, throw a decimal at the end. It's a nice little trick. It's going to help you out. The other one I would suggest is scientific notation, because as soon as you put that decimal down, all those digits are going to become significant digits. So it's going to be a great tool for you. Again, depending on your teacher, maybe they don't want you to do that. Maybe they consider it cheating. I consider it wicked smart. So do what you got to do. With number 4 here, zeros to the left of the first digit are not significant. So notice here now, we have a decimal number. And we have all these zeros in front of these 2 digits here, 8 and 5. Well, all those decimals are considered not significant, which means this number, in fact, only has 2 sig figs. You could think about the fact that we could convert units as much as we want. We could take this 0.0085 and we could convert it into 85 10,000ths of something, and all of a sudden we still only have 2 sig figs. So those zeros in front, not really important at all, so they're not significant. But in the case here, with number 5 and a decimal number, zeros to the right of the last digit are significant. Well, that makes a whole lot more sense. So these zeros are to the right of 2 and 5. Well, 2 and 5 are definitely significant, but in this case, these other 2 zeros actually add to the precision of your numbers. So in our case now, we're looking at a value with 4 significant figures. So a little tricky. Again, this isn't the first time you've seen sig figs, I hope, which means these are more review than anything else. So again, I would base a lot of your future work on this easy table just to get an idea of, are you counting the correct number of sig figs. Now let's go on and let's see if we can do these very simple examples. So we're looking at a number 1500, no decimal. First 2 values, the zeros to the right don't matter, 2 sig figs. In this case, the zeros in between values, which means 4 sig figs. The zeros to the left don't matter, which means we're looking at 2 sig figs. Again, same idea. What the heck? Still 2 sig figs. In this case, number 5, there is no decimal. This is not a non-decimal number, which means there's only 1 sig fig because all those zeros to the right don't matter. What would happen if we put the decimal down? Well, then we'd have 5. So again, be very careful about what you're looking at. Number 6, well, we see that there's zeros to the right of a decimal number, which means those are all significant, which means we're looking at a value of 3 significant figures. Number 7, all those zeros don't matter. These 2 digits definitely matter, and the 0 is to the right. It also matters. We're looking at 3 sig figs. Number 8, this is what I'm talking about. We have a decimal now, and we have these zeros, and the question is, are they significant? Absolutely they are significant. In this case, we're looking at 6 significant figures. As soon as you start throwing decimals down, you are suggesting that your precision is to that number of decimal places, and you have all these integers to the left of the decimal place. You're saying something when you do this. So again, when you're doing labs especially, I would be extremely careful on writing these numbers down. If you write it like the calculator, you're saying something that is more than likely not true, and the best measuring devices on the planet couldn't be as accurate as what you're claiming. So be careful, my friends. Now, we did this idea of significant figures. Now we got to deal with it when we're playing around with the numbers and we're doing some arithmetic. So the first thing we're going to look at is multiplying and dividing. And it's a pretty simple rule. When you multiply or divide numbers, our final answer is always rounded off to the least number of sig figs. So what does that mean? Well, let's take a look. We have these three examples. In the first one, this number here has 2 sig figs, of course. 0 to the right doesn't matter. And this one has 3 sig figs, which means our answer is going to have to be rounded off to 2 significant figures. So if we actually did this multiplication in your calculator, you should get 402.5. Well, how many sig figs would that have? Well, that has 4. That's not okay. We need this to be to 2 sig figs. So to 2 sig figs, this is where that whole scientific notation idea comes up real nice, because now what can we do? We can rewrite this as 4.0 times 10 to the power of 2. Now, why would I do it like that? Well, let's take a look. If we wrote it as 400 with no decimal, that would be only 1 significant figure. If you put a decimal after 400, that would be 3 significant figures. It's a bit trickier one to do. Now, again, is there a way to do it? Sure. What do I recommend, though? Scientific notation. That's why we learn it, my friends. Let's use it. Let's take a look at number 2 and 3. Again, pause and work these out yourself. It's good to know. 2 here, there's 4 there, which means our answer is going to have 2 sig figs. We use the calculator for this, and we end up with 3.0 times 10 to the 4. 3.0, absolutely, because if you do it, you would end up with 30,000. And again, that only has 1 sig fig. How do you get it to 2? There's 1 sig fig, there's 2, and the times 10 to the 4 is irrelevant to the significant figures. What about number 3 here? Well, all these digits count, so there's 4 there, there's only 1 there, which means our answer has to have 1 significant figure. And boy, I'm going to go ahead and say, if we did it with a calculator, we'd end up with this. Well, boy, that still has 4 significant figures. Well, what do? Well, you have to round. And this is going to round to, you could either do 3 times 10 to the minus 1, or you could do 0.3. Either one of those has just 1 significant figure. So be very careful, especially on those multiple choice tests, friends. They try to trick you with that. Now, addition and subtraction, slightly different rule, not overly difficult, but what you need to do is you just need to make sure that your answer has the same number of decimal places as the number with the least number of decimal places. Well, what do I mean by that? Well, let's take a look. We have 25 plus 57.65. If you add this in the calculator, you're going to get 82.65. Now we have to find the number with the least number of decimal places. Well, this one has none. This one has 2, which means we need to match this number, so there should only be 0 decimal places, which means this will round up to 83. If we take a look at number 2, there's 4 decimal places, there's 3 decimal places. When we actually do this math in the calculator, we end up with 0.3481, but we only want 3 decimal places, so this is actually going to go to 0.348. And finally, we take a look, 3 decimal places, 2 decimal places, which means our solution has to have 2 decimal places. With the calculator, we get 0.014. We only want 2 decimal places. Let's round. That 4 does nothing. You end up with 0.01.